In this video, I will illustrate how to perform logistic regression using TensorFlow keras. Now, remember when doing logistic regression, your output variable must be a binary variable. So the values for your output variable must be either 0 or 1 already in the dataset. If your data does not have such an output variable, you can either do some pre-processing cleaning within a notebook by using the Linux backend or some other techniques to convert the output variable into 0, 1, or you can pre-process the variable, the entire data set somewhere outside before loading into Google Colab to convert the output labels to 0 and 1, because the whole idea of logistic regression, which is a classification technique, is to predict whether something belongs to a positive class or not, and basically predict a probability for that class. So let's see how to do logistic regression using TensorFlow keras.
Once again, I'm going to use the PyMath diabetes dataset. And here the question that we would like to ask is, knowing all the input variables, that is someone's age, blood pressure, BMI, etc., can we predict diabetes? That is, can we predict a probability of whether or not somebody has diabetes given all the input variables? I'm going to start by downloading the dataset once again. So we have pymathdiabetes.csv. The next thing that I would like to do is check the first few rows of this data to make sure everything looks okay. So I can see that everything looks fine. What you want to really notice is that the output variable that we have is actually all zeros and ones. I want to make sure that all the values in the output variable are all zeros and ones. So I can do data, and then I can select outcome and then do unique to see what unique values does this variable have. And it does indeed have 0 and 1. So it makes this outcome variable a good candidate as the output variable, because in logistic regression, our output is to predict the probability between 0 and 1. So the output labels must be either 0 or 1. So now that we see that everything is okay, we can load the data set into a NumPy array. Now I would like to check the number of rows and columns in this data set. So I'm going to do print dataset.shape. So it has 768 rows and 9 columns. I would also like to once again make sure that the number of the data points I have is looks legitimate. So I'm going to print, give me the first 5 rows of my data. So we can see that the last number actually is a 1, and we have all of these floating point numbers. To make this look visually clear, I'm going to set the NumPy print precision to 0.1 or 0.2 floating points. And I can do this by changing the np.set print options. Now, if I do my print data set again, the numbers look much more visually clear. And these are my first few rows. The last column still is the output variable. Now, what I would like to do is I would like to create a variable called x that has all the input variables. So data set, give me all rows and everything except for the last column. And in the variable y, I would like to keep all the output variables. So give me all rows and in the last column. So I would like to make sure that this is what I have. I print x.shape and y.shape. So y should only have 1 column, x should have 8 columns total. So x has 768 rows and 8 columns, and y is a list of 768 values. This is good. Now we will do the regular stuff. Let's import the sequential and dense classes from the TensorFlow keras library. And then I create a model equals sequential. Then we add the first layer to the model.add. We would like to add a dense layer with 1 neuron in it. And my input dim is equals to, we have 8 variables, so I can set input dim equals to 8. I can also do here len and then give me the first row and all columns. So this len x 0 colon also gives me the length of, that is the number of input variables I have. And then I do activation equals sigmoid. I do sigmoid because this is a classification problem, and we would like to predict probabilities or numbers between 0 and 1 as the output. So if I put here linear, this is still going to work, but I'm not going to get the kind of results I want, because linear will try to give equal focus between all the values between 0 and 1. So your model will not become a classifier, it becomes a regression model. For classification problem, we want this to be sigmoid. The next thing we do is we provide parameters to the model.compile. And here it is very important that we provide loss as the binary cross entropy. And binary cross entropy, as you may have seen from the chapter notes, this is the standard loss when we have binary classification problems. So we're always going to choose binary cross entropy when we have sigmoid as the activation, particularly in case of binary classification. And then we choose a standard optimizer. And now as metrics, we choose usually accuracy as a metric. This is a standard metric that we can use for evaluating a binary classification model. So I compile the model, and then the next thing I will do is call model.fit. So I have my x as my input x, my output y is capital Y, and then say I choose epochs as something like 256, and then I choose verbose as 1. So let me run the model.fit function. So my model is training. I can see that the loss is going down, which is pretty good. And it has trained, my loss is all the way down to 0.55. So let me retrain this to see if the loss even further goes down. I see that the loss went down to 0.52 again. So let me further train this. Actually, let me increase this to 512 epochs and then run it to get as less loss as possible. So my loss is around 0.49, 0.50. I think I am happy here. Now, the next thing that we would like to do is see or check how the model did. So I know that my true labels are print. Let me see why. Let me print the first 5 values of the true labels, and these are my true labels. Let's see how the predictions for this look like. So I can do predictions equals model dot predict, and then I'm going to supply x as input. So these are my predictions, and let me see how the predictions look like for the first 5 values, for the first 5 inputs. So my predictions are actually better visualized with the transpose. So I'm going to transpose this. And we can see that for when the actual output was diabetes, our model predicted diabetes with a confidence of 0.6. When it was not diabetes, it predicted diabetes with a confidence of 0.1, which is a correct prediction. I mean, overall, it's correct. For this case, it predicted diabetes with a confidence of 0.8, which is very good. And then for this one, it predicted with a confidence 0.1. So this confidence, again, is below 0.5. So this is actually also a good prediction. So here, the output is actually 1, and our model predicted diabetes with a confidence of 0.9. So all of these are, in a way, correct predictions because your model is producing high probability, more than 0.5 for true cases, and low probability for the cases where there is no diabetes. So our model is actually doing a good job. We can actually further increase this to 10 and see how the model is doing for the rest of the 5 predictions as well. So here, actually in the last case, the output is 1, but the model predicted with a very low probability. So in this case, the model actually failed to make the correct prediction. Even here, the model failed to make a correct prediction. Oh, actually, even here, the model failed to make a correct prediction. But over here, the model made a very good prediction. Even on this one, the model made a good prediction because 0.2 is actually 0.2 probability is very low probability for something that's a negative data point. Besides using accuracy and precision and all those metrics that we saw, this is a very good way to check how your model is doing on the data set that you have used to do the training.